works for Red Hat and has been working in open source for a long time, contributing to a number of projects whose names you would recognize.
A couple of years ago, I started doing Kubernetes stuff, and I wanted to really understand how Kubernetes worked. So Kubernetes is sort of the cloud, the de facto cloud operating system, I think you can say at this point. And but when I first started doing it, all the instances I was working on were one node instances. So overlay networks and stuff like that were kind of didn't matter, right? Because it was on the same network. So I started building a little cloud. I was one of the first ones to do this using 4 Raspberry Pis and having Kubernetes, having 1 master and 3 nodes to do the work on. And, okay. And this was a lot of fun, and I learned a lot of stuff doing this, right? Because now you actually have 3 different physical boxes, and you actually have to have an overlay network across these nodes. But while I was doing this is kind of a play thing, right? And it's just for learning purposes, but it's not really, doesn't have enough horsepower to actually run a serious application on. But it uses very little power. And this kind of got me thinking, like why, a lot of applications we write are not working all the time, right? There's a lot of standby time. There's a lot of energy wasted of systems that are just waiting for things to happen. What if we could really build real cloud instances using ARM64 architecture? So I started looking into, what does that mean? Well, obviously there's 2 points, right? First, you need to run all your infrastructure, your Docker, and your Kubernetes on ARM64. So you need to have the binaries for those two pieces. Secondly, you're going to have to rebuild all your containers, right? And so I started on this first point. I kind of was there already, right? But the second point is what this presentation will be about. How do you go about rebuilding all your containers? Because you don't really want to double all the work you're doing. That's going to be a beast. So I started project 31. So on GitHub, there's a project 31. It's roughly pi cubed is 31, right? So hence the name. In it, I'm describing how to get CentOS 7. I'm from Red Hat, so I like the CentOS distribution. I'm familiar with it, but even more so, Red Hat distributes it in RPMs, right? So if you can get CentOS on your board, there's an RPM for Docker, there's an RPM for OpenShift, and I've been bugging them so that they actually make this for alternative architectures, so for ARM64 as well. So all you have to do is once you have the base ARM64 CentOS 7 board running, you add another repository that points to the alternative architectures that are not publicized, right, at the moment, because we don't want to support ARM64 at the moment as a company, but we do make it, and we publish it. So all you have to do is add another repository. There's the iPaaS repository, and you get all the extra RPMs. So you can get Docker and you can get OpenShift. You enable it, and you're off to the races. So now you do yum install OpenShift, and there you go. So at my home right now, this is the Raspberry Pi 3. This is what I started with. It's 1 gigabyte of RAM, 100 megabit bus network bus. So it works. but it's not very fast. If you want to do anything, you're going to wait for I/O, and you only have 1 gig memory to do anything on. These are Pine 64 boards. So it's 64-bit. It's 2 gigabyte of RAM. It's a gigabit of network connection. This is a pretty decent computer. So I have 7 of them here in one stack. 7 times 2 is 14 gigabyte of RAM. I have a gigabit switch sitting underneath. And each board has a little micro SD card. This one is 32 gigabyte, but they make them up to a half a terabyte now, which is just insane that it's like, as big as your nail. And it's got OpenShift on every node, and it's humming along. Cool, right? So this is what I have, basically. The things in red is the hardware. So I have a master, and then I have a couple of nodes, and each node runs pods. The pods deploy the containers. So on the right, you see the registry. The registry could be Docker Hub if you want to do it publicly, or you can have a private registry. So that contains all the images. So now we're going to point number 2, right? Yeah. Cool.
Just a rough cost of that picture.
Oh, yeah. Cool. It's $29 for a board. The SD card is about $10. What else is in the picture? There's the switch. Cost of that is, I don't know, $20 for the gigabyte switch. There's 2 boxes of Mint that are empty. That I use a double-side tape to glue onto the switch. Yep. So I didn't have to drill holes in the switch. Okay. And then I could just drill holes in the pins and use those little connector thingies to set the boards. You can get those at the hardware store.
$400, less than $400.
Oh, it's less than 200. Well, yeah. Cool. So it turns out that as far as base images go, a nice example would be to go on Docker Hub to multi-arc Alpine. Alpine is the smallest image around, so it's fun to use that because then for demo purposes and stuff, it's small, so it's easy to move around. And the multi-arc organization has done a really nice job that they've put out Alpine base images for different architectures, right? So there's a regular ARM, there's an ARM64, and this is the regular Intel image. The distribution is identical. It's a Linux distribution, right? But the binaries on the images are slightly different, right? They're targeted towards the kernel, the kernel's architecture, which is different on Intel than it is on ARM. So you do have different binaries within these images. But if you look at it from a file system perspective, everything looks the same. All right. I think it's because I'm standing on it. So how do you manage this, right? How do you manage these different images? The Docker community has been handling this, and they've come up with a manifest command. So there's a Docker manifest command about to come out. It's not in the current Docker command line tool yet, but it is there if you turn on beta features. So if you turn on beta features, then you can use this. What that means is I can create a manifest, which is just like a regular image, but it isn't an image, it's a pointer to other images. God, I'm not standing on anything now. So, you can create a manifest that is identical to the name of the distribution that you want to run, right? And in it, it references the Intel image, and it references the ARM image. And at the time where you tell the Docker daemon, I want to run this, and you send the manifest address, it then turns around and says, oh, what architecture am I on? Oh, I'm on ARM architecture. Let's grab the ARM bits, the ARM layers. So it just pulls in the ARM layers. It's not like the manifest makes everything twice as big. It knows I'm on ARM, so I only need the ARM layers. All right, so what does that look like real quick? Let's see if I can switch this. I'm going to make this a little smaller, otherwise there's nothing on the screen. This is in manifest, and we're going to inspect it. Let's start from the top. So you see there's a whole bunch of ones. So that's architecture 1, and it references an ARM64 kernel architecture, right? And then if I scroll further down, there's a second set of layers here, and then with 2s in front of it. This is an ARM64 architecture. And so there's two different architectures in this manifest. And I guess I could say Docker run it. And then the name of the manifest, project 31/Docker open VPN. And then latest, I guess, but latest is whatever it is. And it is on an Intel machine now. So it pulls down the correct layers. And oh, I forgot to tell it what process it should be running. Let's do bash. Yeah. So now I'm logged into the container. So I didn't really do anything from my client. From my client, I didn't change anything, right? As long as I reference a manifest, it figures out for me what architecture it needs to download. That's kind of cool. All right, still didn't solve my problem of building it, right? Because I still would need to build. Let's minimize this. All right, let's get rid of it altogether. Let's go back to my presentation. Cool. So we've done manifest, right? So what it looks like on Docker Hub is that the repository project 31 Docker Open VPN, and then I'm using the tag to name it with the architecture that it is, so that as a human I can see this as well. So those are the tags, and then this latest one, this is the manifest. All right, so what I have in a company, we use CI to build our images. So every time I do a pull request in my project, it knows to go build Docker containers for me. You can use any of these CI systems. You can even build on Docker Hub if you want, but my example will be on Travis. So this is a little hack. So remember QEMU, virtualization? So if you run a virtual machine, QEMU is doing all the translations for you, right? So if I build a binary, let's say with Go, you can really easily build binaries for different architectures. So here I'm building a hello world thing, and I'm building for an architecture of ARM. So now I'm getting the hello program, the executable, with an ARM architecture. If I execute this on Intel, it won't work, except if I prefix it with QEMU ARM static. So the static library of QEMU sits in front of the process that I'm going to execute. That will work, right? Okay, cool. So let's take this one step further. In the Docker file, anytime I'm going to do run, I'm going to prefix that with the static library. So any command that's going to get executed in my Docker container is going to get translated so that I can actually execute ARM binaries on an Intel machine. But it looks kind of nasty to do it this way, right? My whole Docker file looks different because I have to prefix it all the time. So what you can do is put a shim in. You know why they call a shell a shell? The shell is called a shell because it's the closest thing to the kernel. It surrounds the kernel with a thin shell. Every command that you execute goes through the shell. So the sh binary is the closest thing that sits to the kernel. What if I can tell it, anytime you execute something, prefix it with my static library call? So what I'm actually going to do is I'm going to switch out the sh binary, replace it with my little script, right? That does calls the QEMU binary, and then it does whatever command I was going to give it. Okay, so that's called cross-build start. So in my Docker file, I can now say, well, from this image, that's an ARM image, run cross-build so that I have the shim in place. Now I can run whatever Docker commands I want to run, and then at the end I take the shim back out. Otherwise, it's not gonna work, right? And now the final product is an ARM container. Wow, that's kind of cool. So now I can use this trick to build anywhere, as long as I ship a QEMU static binary in my ARM image, in my base image. Okay, so now I'm going to go to Travis. And Travis has a nice flow command. And what I'm going to script is three builds. Right, the first build is an ARM, and the first build is an Intel build. The second build builds the ARM image, and then if both are successful, it builds the manifest. Basically in one go. So what do I have to do? Let's go to my sources. And let's go to the Travis file. So here I'm defining that matrix is what they call it. So for every architecture, I can add a line here in the matrix. And so one line is for ARM and the other one's for AMD. And then I'm gonna build. And the first line that's of interest is here. If it's not an AMD build, execute this. And it's executing a multi-arc QEMU user static thing. So it registers that shim. So I don't even have to do that in the Docker file anymore. I can do it from the outside as well, which keeps my Docker file really clean. So I don't have to have a Docker file for every architecture. Then I run whatever I need to run. These are all the things that the OpenVPN project runs to build that image. There is actually a test phase too. That is still a little bit problematic because they test for over 30 minutes. And if I add they test a lot of key encryption, which takes a lot of CPU. If you do that over a virtualized ARM image, it takes over an hour, and they cut you off after an hour. So that's still an issue I have to work on. So I'm skipping the testing now. And then finally, I'm running the manifest command here, the Docker command here to create the manifest command based on the two architectures that I have, and I'm doing a Docker push, so it pushes it right up to Docker. To show you that I really have only one Docker file in here, this is my Docker file. The only thing that's special in here, that is the from image. The multi-arc people don't use the manifest command yet, so I have to actually specify for which architecture I build. So with Travis, I push in, I set the from variable. But everything else is the same as it always was. So this is just, you know, whatever the Docker file for OpenVPN was. Okay. Let's go back to my presentation. What was at the end? All right, so if you want, at the end, I can just run this build so you can see it live building. So you see, I'm not lying, but this is what it looks like. And on this slide, I've highlighted the 4 or 5 lines that are different from the regular Travis file that they already had, and I referenced where you can get a copy. So the conclusions is that we can now build containers for alternative architectures. Like, it doesn't just need to be ARM, it could be anything, using our current CI infrastructure. With the Docker manifest, we don't even have to update our documentation, because if we name the manifest what the original name of the Intel image was, then everything stays the same. It's just a reference at that point. Kubernetes doesn't need to know what architecture it is. Really, only the Docker daemon needs to know what the architecture is. So if Kubernetes, the master, tells a node what to do, the master doesn't even really need to know about the architecture of the node, the chip architecture, because Docker will figure out to grab the right image. However, you could build a hybrid cloud with different architecture nodes and specify what the characteristics of the resource is, because Kubernetes can be taught to schedule out jobs considering the resource constraints that it has. So you could target it to say, you know, if you're doing a job like this, it takes a lot of memory, put it on these nodes and not on the others.
That would be like any other heterogeneous
Yeah.
infrastructure.
Yeah, but even if you're running 6 nodes, 6 pods on one pod already, and number 2 pod is doing nothing, it knows, oh, number 2 pod, I probably should schedule on now because it's doing nothing, because it knows what the resources of that, the free resources are. All right, so now I can run ARM64 based containers on a Kubernetes cloud, and it's just using less power. And it really, from our perspective as developers, to create these containers, there's really no extra work, right? Yeah, a little bit of electricity to build more containers, but I don't have to like replicate all my CI infrastructure. I can leave it on Intel. Yes.
What's the magnitude of energy saved?
Well, it depends, obviously, but the ARM chips are designed for phones, And so the number one design criteria is low power. And so it's in the order of 10%, I would say, compared to Intel. So, typically these boards, they draw about a watt and a half. So it opens up the way to power them, the solar panels. I actually have batteries at home, lithium-ion batteries, which I was going to bring to power these boards, but you can't fly with them anymore. So I left them at home. So yeah, but it also means that if you only put a watt and a half in, you don't need huge cooling facilities either. Yeah, yeah. So yeah, I think you are the architects. You should see this coming, because I think it's up to you to make the decision for what chip architecture you're going to go for, and then you can influence people to say, maybe we should buy an ARM machine, and they don't have to be these boards. There are already machines that have 96 cores with 320 gigabyte of RAM, big boxes basically for data centers, and they use 10% of the power. Plus, they're about 10% of the price, because we're making chips for phones, and we're making so many of them, the economy of scale works there.
Also, think about Internet of Things, and you want to maybe do some aggregation further out of the data centers, so having small cloud-like kinds of things.
Yeah.
And start doing ingest and pre-processing. So I've got some colleagues who are working on those kinds of architectures.
Yeah.
And this would be a nice enabler and simplifier.
Yeah, but there's not any data centers that I know of that run ARM architectures, but I would think that wouldn't be far away. Thank you.
Questions?
Can you recycle old phones to really be Docker?
Can I recycle what?
Old phones, like a little thing, like they already have like old Docker containers.
I don't know. They're only $29, so it's probably more work than it's worth. Yeah.
Well, Kurt, thanks for stepping in and providing the demo for us.
You're welcome.